Hello everyone. So in this video I'm going to go over significant figures. So what are they? Why do we need them? How do we use them? All of that and more is going to be covered right here in this video. So before defining significant figures, I'd like to talk a little bit about why they're important. And the reason why they're so important is because precision must be preserved. So what do I mean by that? Well, in my last video I talked in great detail actually about how to report scientific measurements. And one of the things that I mentioned in that video was anytime you report a scientific measurement, the number that you report is going to reflect the sensitivity or the precision of the scale that was used to make that measurement. So not only does this precision have to be preserved in the measurements themselves, but it also has to be preserved when we make calculations involving those numbers. So that's where significant figures come in. What significant figures do is they add to the certainty of a measurement. So that means that the more significant figures you have, the more certainty there is associated with your measurement. Significant figures are non-place-holding digits, meaning they do more than just mark the decimal place. And the nice thing about significant figures is that all non-zero digits are considered significant. So the only distinction that you have to make in terms of counting significant figures, like how many significant figures does this number have, is going to have to do with zeros. So some zeros are significant and some are not. So for instance, in the number 0.000004, these zeros that come before the 4, the only reason why they're there is to just mark this decimal point here, so therefore they are not significant. On the other hand, if I have a number such as 0.004000, these three zeros here that come after the 4, they don't necessarily need to be there, so they're not just marking the decimal place, so therefore they are considered significant. So let's go through all of the rules associated with how to determine whether a zero, any given zero, is significant or not significant. The first rule that I'm going to go over has to do with interior zeros. Interior zeros are zeros that are located between two non-zero digits. Interior zeros are always going to be significant. So for instance, in the number 8.092 meters, the zero, which is located between two non-zero digits, is significant. The next rule has to do with leading zeros. So by leading zeros, I'm talking about zeros that come before or to the left of the first non-zero digit. Leading zeros are not significant. So what do I mean? For instance, in the number 0.00237 grams, these three zeros here that come before the first non-zero digit, which is the 2, are not significant. Now let's get into trailing zeros. So by trailing zeros, I'm talking about zeros that come after the last non-zero digit. And there's a couple of different rules associated with trailing zeros. First of all, if the trailing zeros occur after a decimal point, so to the right of a decimal point, they are significant. So for instance, in the number 4.00 degrees Celsius, these two zeros, they trail the last non-zero digit, but they occur after, to the right of the decimal point, therefore they are significant. If trailing zeros occur before an implied decimal point, then they are not significant. So what do I mean by an implied decimal point? Well, in the number 6,000 Kelvin, there is a decimal point understood to be right here after this 0, although it is not shown. So if the decimal point is implied but not shown, then the zeros that come before that decimal point, if they're all trailing zeros, then they are not significant. Now, if trailing zeros occur before an actual decimal point that is shown, then they're significant. So if I have 6,000 dot Kelvin and the decimal point is actually shown here, now these three zeros can be considered significant. So there is all the rules on how to determine whether a zero is significant or not, and remember that non-zero digits are always significant. So the next thing I'd like to talk about has to do with exact numbers. So exact numbers have no uncertainty associated with them. Therefore, they have an unlimited or infinite number of significant figures. So a couple of examples of exact numbers. Well, one of them is when we count discrete objects. So in other words, if I have 3 apples, I have exactly 3 apples. I have 3.000000, infinitely many zeros, and they're all significant because I know that I have 3 apples. That's not based on any measurement. That's counting a discrete object. That's an exact number, infinite significant figures. There's also another example of exact numbers is defined quantities. So for instance, the conversion 1 kilometer is equal to 1,000 meters. This is true by definition. This is just something that a human being came up with. So therefore 1 kilometer is exactly 1,000 meters, and these numbers have an unlimited number of significant figures. The third kind of exact number is an integral number within an equation. So for instance, the volume of a sphere is equal to 4/3 pi times the radius cubed. Well, this 4/3 pi here, this is going to have an unlimited number. Well, the pi especially is going to have an unlimited number of significant figures because it's a non-terminating decimal. But the 4/3 here, this is going to have an unlimited number of significant figures as well, because this is an exact number. It's an integral part of an equation. So again, unlimited number of significant figures. So with that, let's get into a couple of examples and see if we can't count how many sig figs there are. Sig figs is just short for significant figure, so I'm going to use the term sig fig from now on. How many sig figs are in these next few examples? Starting with 7.3278 kilograms. How many sig figs are in this? Well, the nice thing about this one is that these are all non-zero digits, so that means that they're all going to be significant. So there's 1, 2, 3, 4, 5 of them, so this has 5 sig figs. Kid stuff. Let's go on to a slightly harder one. This one is 0.0304000 moles. So how many sig figs are in this? Well, this one has a lot going on in it because there's 3 different kinds of zeros. We have some leading zeros over here. We have an interior zero here, and then we have some trailing zeros over here. So if you remember the rule, leading zeros are not significant, so we're not going to count these two. Interior zeros are significant, so we're going to count this one. And then trailing zeros, if they are after to the right of a decimal point, then they are significant. So we're going to count all the digits from this 3 all the way to the right. So there's 1, 2, 3, 4, 5, and 6 sig figs. So let's go on to the next one. Next one says we have 0.0000000000008 seconds. How many sig figs does this have? Well, as I touched on in the last example, leading zeros are not significant. So this whole mess right here, all of these zeros, none of them are significant. The only number that is a sig fig out of this entire thing is the 8. So therefore, this has 1 sig fig. Let's go on to the next one. The next one is 3.72 times 10 to the negative 12 candelas. Candela is the SI unit for luminescence intensity. When it comes to numbers that are shown in scientific notation like this, you can basically just ignore the power of 10 and just focus on this part here on the left. So if we look at this part here on the left, well, they're all non-zero, so they're all significant, and there are 3 of them. So this has 3 sig figs. Next one, it says we have 1.004 times 10 to the 26 atoms. Okay, so you might say, all right, the 1 and the 4, those are non-zero, so those are significant, and then these 2 zeros are interior, so they're significant. So this has 4 sig figs, right? Wrong. The reason why this doesn't have 4 sig figs is because we're talking about atoms here. We're not talking about a quantitative unit of measurement, right? So when it comes to counting discrete objects, which is what I mentioned in the last slide, these are exact numbers, so they have an unlimited or an infinite number of sig figs. So the next example says we have 400 dot coulombs. Capital C, that is the symbol for coulomb, which is the SI unit for electric charge. So 400 dot coulombs, how many sig figs does this have? Well, when you have trailing zeros that come before an actual shown decimal point, then they are significant. So this has 1, 2, and 3 sig figs. So the next example says we have 70,000 amperes. The ampere with the symbol capital A is the SI unit for electric current. And remember, if the zeros occur before, to the left of a an implied decimal point, then they are not significant. So that means that all 4 of these zeros are not significant. The only one is a 7. The only one that is significant is a 7, so that means we have 1 sig fig. So the last example that I'm going to do is 1 femtosecond is equal to 10 to the negative 15 seconds. So again, this is a man-made definition. This is a man-made relationship, so it is true by definition. So that means that these are exact numbers and they have an infinite number excuse me, of sig figs. So with that, let's get into how to use significant figures in calculations. So when it comes to addition or subtraction, whatever result that you get is going to carry the same number of decimal places as whichever quantity you have that has the fewest number of decimal places. So for instance, if I have the calculation 6.005 grams plus 4.1 grams, the 6.005 grams goes out all the way to the thousandths place, and the 4.1 grams only goes out to the tenths place. So that means my result is going to be rounded to the tenths place. It is the lesser of the two of those. Now when it comes to multiplication and division, whatever result I get is going to carry the same number of significant figures as whichever quantity has the fewest number of significant figures. So in other words, if I have the calculation, for instance, if I have 3.11 meters times 5.092 meters times 6.3 meters, well, which one of these has the fewest number of sig figs? Okay, this over here has 3, this over here has 4, that interior 0 is significant, and then this one over here has 2, so that means that I'm going to round whatever my answer is, I'm going to round that to 2 sig figs. So I'd like to talk a little more about rounding now. And you may already know how to round numbers, but I'd like to just go over it a little bit just so we're all on the same page. And so basically, if it's less than halfway, you're going to round down. So in other words, if I have 3.224 and I want to round that to the hundredths place, so that means this 2 here is the digit that I'm going to round. Do I round off the 4 and keep it as a 2, or do I round up and make this a 3? Well, it's less than halfway. This 4 it means that it's less than halfway between the 2 and the next digit up, which is 3. So I'm going to round that down to 3.22. Now, if it's more than halfway, you round up. So if I have 823.63, and I'm going to round that to the ones place. So now this 3 here in the ones place, that's the digit in question. Do I keep it as a 3 or do I round it up to a 4? Well, the next digit following the 3 is a 6, so we definitely know that this is more than halfway between the 3 and the 4, so we're going to round that up to a 4. Notice how I kept the decimal point there. Now, this next rule isn't necessarily agreed upon by everybody. I wish there was a universal way that everybody taught this, but unfortunately there's not. But the way that I was taught it is the way that I'm going to teach you now. And that is that if it's exactly halfway there between the two digits that you're considering rounding to, then you're going to round to the whichever digit is even. You're going to round to the nearest even digit. So in other words, if I have the number 7.8785, and I'm going to round this number to the thousandths place, so this 8 here, that's what I'm thinking about rounding up or leaving it as an 8, that's actually going to go to the nearest even number. So it's actually going to round down to the 8. And if you think about it, this makes a lot of sense, because if it's exactly halfway there, then there's really no reason why. I mean, I know that a lot of you would probably round up in this case. That's what we're taught at a very young age. But if you think about it, there's really no reason, if it's exactly halfway there, there's really no reason why you should round one way up. There's really no reason why you should round up every time and then round down none of the time, because again, it's exactly halfway between the two. So the way that this is usually avoided is by rounding to the nearest even number, which also makes calculations a little bit easier, because keep in mind, we didn't always have calculators. So before we had calculators, we had to do these things in our heads. We had to do them by hand. And when you were working only with even numbers, or with as many even numbers as possible, that made your calculations easier. So on the other hand, though, if I had a number such as 7.875000001 and I wanted to round that to the thousandths place, it doesn't matter how far removed this 1 is, it's still a little over halfway. So that's actually going to round up. That's going to round to 7.879. So one last thing about rounding, and that is when you have calculations that involve more than one step, you're going to round only to the final answer. You're not going to round any of the intermediate steps along the way. You're still going to keep the same number of significant figures for each one, so you want to keep that in mind as you continue through your calculation, but you don't want to round until you get to the very final answer. So with that, let's get into a couple of examples. So the first example is 4.5338 milliliters plus 100.2 milliliters. So what is this? So if you stick this into a calculator, the calculator is going to spit out this. The calculator is going to spit out 104.7338 milliliters. But we're not going to keep all of this, right? We're only going to keep some of it because we want to apply the rules for addition and subtraction, which is you want to keep your result is going to carry the same number of decimal places as whichever of these two quantities has the fewest number of decimal places. So this one goes all the way out to the 10,000th place right here. This one only goes out to the 10th place, so that means that my result is going to go out to the 10th place as well, and the 10th place is right here, so this is the digit that I need to round up or I need to keep the same. And since this next digit is a 3, I'm going to round that down, and it's going to be, our final result then is going to be 104.7 milliliters. So now let's move on to another example. And the next example says we have 4.24687 times 10 to the 21 kilograms. And we're going to multiply that by 9.8 meters per square seconds. So how do we do that? Remember, this is a multiplication problem, so we're gonna instead of doing it by decimal places, we're going to do it by significant figures. So if you put this into a calculator, then the calculator is going to spit this at you. The calculator is going to say, I got it here. It's going to say 4.1, whoops. 619,326 times 10 to the 22, and the unit is kilograms times meters per square seconds. So again, this is a very long-winded number, and we're not going to keep all of this. We're only going to keep some of it, and the way that we do that, again, with multiplication and division, is we go by the fewest number of significant figures. So this has, this number on the left here, this has 1, 2, 3, 4, 5, 6 sig figs, and the number on the right has much fewer. It only has 2 sig figs. Therefore, our final number is going to have 2 sig figs, so therefore it will be 4 point, we're going to round this guy up because 6 is greater than halfway there, so this is going to be 4.2 times 10 to the 22nd kilograms times meters per second squared. And the interesting thing about this is that kilograms times meters per square seconds, this is actually newtons. So 1 newton is equal to 1 kilogram times meters per square second. So 4.2 times 10 to the 22nd newtons is also a correct way to express this. So let's go through one last example, and that example is, okay, so here it is. We have 9.249199 grams minus 9.1 grams, that quantity, divided by 57.84 milliliters. So how do we do this? Well, the order of operations that you learn in like 4th grade math tells you to do parentheses first, so we're going to carry out this top operation first, right? So if we subtract everything, if we subtract this really long number here by this really short number here, then that's going to give us, let's see, that's going to give us 0.149199 grams, and that's going to be, again, divided by 57.84 milliliters. Now again, we don't want to round this yet because we're not done. We only want to round when we get to the very end. However, we want to keep the number of sig figs according to the rules associated with addition and subtraction, which is to take the fewest number of decimal places. So this goes way out here. This one over here only goes to the tenths place. So that means whichever number of sig figs that we're going to keep when we do the next calculation is going to be just to the tenths place. So this is actually going to be, we're going to cut this off right here. I'm just going to put a line over it. So that means we are going to carry it out to this place right here. So that means that when we carry out this next calculation, this division here, we're going to assume that this has one significant figure. It only goes out to the tenths place, 1 sig fig, and then this one only over here has 4 sig figs. So when you divide this number by this number, you will get 0.0002579 and the unit is grams per milliliter. So now that we're, this is our final operation. Now we're done. Now we can round. So the question is, where do we round? Well, again, we're going to assume that this has one significant figure because of the previous calculation. It stops right here. So one significant figure, 1 sig fig versus 4 sig figs. That means we are going to keep this to 1 sig fig. So that means that we are going to round this 2 here. Well, this is more than halfway there, so we're actually going to round this 2 up. So we're going to round this to 0.003 grams per milliliter. So that, in a nutshell, is how you use significant figures in calculations. I hope this video helped you out a little bit, and if you have any questions, please feel free to comment me down there, or send me an email on my website, or post a comment on my channel, or however way you want to do it. All right, have a good one.